This is my homebrew 8-bit CPU. It has a memory that stores the program, a program counter that steps through the instructions in the program, an arithmetic logic unit that performs computations, and on the left 7 registers to store intermediate values. And when I power this up and hit run, the program will do a few checks and then compute the largest 16-bit Fibonacci number, which turns out to be the number 46,368. Now the CPU is already pretty capable, it can do quite a few interesting things, but it doesn't really do any instruction decoding. Instead, each instruction has 16 bits, and we've connected the instruction bits more or less directly up to the control signals of the CPU. So every instruction specifies pretty directly what each of the components of the CPU should do. This is pretty inefficient though. For example, the lowest 2 bits of the instruction are used to control what the program counter does, if the program counter should step to the next instruction or if it should perform a jump to some address. But those bits are really only used by jump instructions. And similarly, the upper 4 bits are directly connected to the opcode input of the ALU. But those bits are only useful for ALU instructions to specify. And so in a sense, we're wasting a lot of instruction encoding space. If you consider a jump instruction, for example, it doesn't do anything with the ALU result, it just discards it, but still it can specify exactly what the ALU does with the upper 4 bits in the instruction. So in theory, there's a dedicated jump instruction for every single ALU operation, but they all behave the same way because the ALU result is not really used. This isn't really a big issue right now because the CPU is pretty simple. But once we add more and more functionality, we're going to need more and more instruction bits to control the new pieces of the CPU. To fix this issue, I think it's time to look at instruction decoding. My CPU currently encodes instructions as follows. 2 bits control the program counter, whether it steps to the next instruction or jumps. 1 bit selects between an ALU operation or a move. Bit 3 indicates whether the second operand is an immediate extracted from the instruction bits, or just a regular register operand. Bits 4 through 6 encode the destination register RD. Bit 7 indicates whether we're writing to RD. Bits 8 through 15 are used as an immediate value for immediate operations on the one hand, but bits 8 through 10 are also used as the second register operand RS. Bits 11 through 15 also serve as the ALU opcode, and we've been using bit 11 to indicate whether we should write to the flags or not. The problem with this encoding scheme is that we have some redundant operations. Consider a jump with register, for example. Notice how the instruction specifies both the program counter mode and the ALU opcode. But for a jump relative, only the program counter mode is really important. And the ALU opcode and whether we're writing the flags isn't really considered because it's not part of the instruction. But the instruction still specifies the ALU opcode explicitly. And since we're ignoring the ALU result, we can pick any ALU opcode here, and the instruction will still be a jump relative with register. To put it differently, there are 32 different encodings for the same jump instruction, one for each possible ALU opcode that we then subsequently ignore. Redundant operations aren't the only problem though, we're also missing out on useful operations. For example, an add with immediate would be nice, and we used to have this earlier on in the build. But then when we added more detailed ALU opcodes, the location of the opcode started clashing with where the immediate bits are in the instruction. And because the immediate bits and the ALU opcode occupy the exact same space in the instruction, we can't have ALU operations with immediate operands at the moment. Processors usually fix this issue by sticking a Boolean function between the instruction bits and the actual control signals of the processor. This Boolean function takes the instruction bits as its input, for example 8 bits in an old CPU like the 6502, and then produces potentially hundreds of control signals for the CPU. This function is generally called the instruction decoder, and it's essentially a compression scheme that allows us to keep only the useful combinations of the control signals and pack them up densely in the instruction encoding space. For example, a processor could have 30 control signals, which gives us over 1 billion different combinations, but maybe only 1,000 of those are actually sensible instructions. We can take these few useful instructions and ignore all the other control signal combinations, and then assign numbers to these instructions starting at 0. And in doing so, we need far fewer bits to enumerate all the different instructions. If we have 1,000 useful instructions, we might only need 10 bits to encode them all. The instruction decoder then is just a function that maps from this number to the full list of control signals that our CPU has. And this mapping back and forth from an encoded instruction space with fewer bits to a decoded instruction space with a lot of bits, one for each of the control signals, is a kind of compression scheme. Instruction decoders come in different forms. This here, for example, is a die shot of the 6502 processor that powered a lot of the early days of home computing, including the Apple II, the Commodore 64, and many more. The Visual 6502 project has a fantastic repository of die shots, schematics, and even an interactive view that runs in your browser that allows you to run a program and then see the actual signals change on the die, which is fantastic. Now in this processor, the instruction decoder sits at the top of the die. It's this regular structure up here. This is very much like the programmable logic device that I used on my ALU for the CPU. The instruction bits and their inverted versions are generated out here on the right, and then they get pushed across this regular structure horizontally. And along with the instruction bits, there are also signals indicating which microstep of the instruction we're executing. If you remember, the 6502 is a processor that takes multiple cycles per instruction to execute. The signals are then combined vertically with these dots you can see. Each dot picks up one of the horizontal signals and feeds it into a transistor, and then all the transistors in the column form a logic gate. It's either an AND or an OR gate, I'm not entirely sure, but these compute different control lines and other information that the processor needs to execute an instruction. And the placement of these small dots is equivalent to the fuses we had to program into the PLDs in the ALU. But in contrast to the ALU, where we can reprogram that programmable logic device, these dots here are hard-coded on the fabrication masks that were used to build the 6502 chip. So in a sense, the 6502 implements its instruction decoder with a kind of programmable logic device or gate array logic. This isn't the only option though. This is a die shot of the original ADDI by Intel. These still power almost all desktop computers today, generally referred to as the x86 processor family. And looking at this, I can make out at least 3 highly regular patterns on the die, which usually turn out to be ROMs, RAMs, or some other form of masked programmable logic. The ADDI was one of the first processors to introduce microcode. It translates an instruction into a sequence of much simpler micro operations that are executed out of a ROM that sits on the chip. And that's how they can have single instructions do unreasonably complicated things. They just spread those things out across multiple clock cycles. Now, the structure here at the bottom right is the microcode ROM of the processor. It uses the current instruction and some other signals as address and produces the value at that location in the ROM. And that value is interpreted as the control signals for the CPU. It's basically a lookup table. So instead of using logic gates to compute control signals from the instruction bits and some CPU state, this simply stores the control signals for all possible instruction bit and CPU state combinations in a large lookup table. Using ROMs is a very convenient and powerful way to implement arbitrary Boolean functions, especially today where you can pretty easily get ROMs storing hundreds of kilobytes, like the one I'm already using as a program memory. We just pre-program the ROM with the outputs we want to see for all possible input address combinations. And I think that's what I'm going to do for my CPU as well. First, let me get rid of this breadboard down here. We've been using an OR gate and an inverter to set some of the control signals of the CPU, but we're going to replace all of this with the decoder. I'm going to use the exact same flash chip as I've used for the program memory, and I think we'll need 2 decoder ROMs to produce a total of 16 bits worth of decoded information. As a first step, let me bring the 16 instruction bits down onto the left side of the breadboards. These chips need power and ground. And then we'll want some bar graph LEDs to look at the data that is produced by the chips. Now, it would be a shame if I added these LEDs and they didn't work, so let me give them a quick try. Pretty nice. As a first step, let me tie some of the control signals of the flash chips to a 1 or a 0. We never want to enable writing, we always want to enable reading, and we always want to enable the chip as a whole. And then we're not using address bits 16, 17, and 18 that these chips have. In the future, we might want to connect those to some status signals of the CPU to influence how we decode instructions under certain circumstances. And the only thing left are the address inputs, which we're going to connect to the instruction bits, and the data outputs, which we're going to hook up to the bar graph LEDs. Let me start with the addresses. So this feeds the 16 instruction bits to the address inputs of the ROM. Now let me deal with the ROM's data outputs. Let's see what this does. It looks like this is doing something. I think I might have flashed the exact same random pattern into both of these chips just to make sure that there's just random garbage in there. And that's why both of them show the exact same pattern at the output. But basically we're taking the 16 instruction bits and we're mapping them to two 8-bit values through these decoder ROMs. And these 16 decoder output bits, we now need to hook up to the rest of the CPU somehow. So let's start assigning some bits. I think I want to use the first ROM to primarily decode the register usage of the instruction. Bit 0 is going to indicate whether we read the RD register, the destination register that we're also writing into. Bit 1 is going to indicate whether we write the RD register. This is useful to distinguish because we had instructions like the compare, which read to registers, but it didn't write back into the register file. Then bits 2 and 3 I want to use to indicate how the RS operand, the other register operand, is used. Up until this point, we've only distinguished whether the second register operand is going to be something we read from the register file, or whether it's going to be a few immediate bits coming from the instruction. But now with the decoder we can actually be a bit more precise. I think I want to use bit number 3 to indicate whether we read the RS operand, or whether we're using the immediate bits from the instruction. And bit number 2 is going to distinguish between 8 and 4-bit immediate modes. And if we're doing a register read, it's going to indicate whether we're using the third read port of the register to read a 16-bit value for the RS operand. We don't really need the information about the 8 or 16-bit read from the register file yet, but it'll be handy in the future. Bit number 4, I want to indicate whether we're reading the flags register. We don't really have a use for that on the CPU today, so I'm just going to leave it disconnected. But in the future, when we're doing hazard detection and making sure that we're only using registers that have already had their value computed, this is going to be a very useful bit. And then bit number 5, I want to indicate whether we're writing the flags. And this we're already using today. And then temporarily, I want to use bits 6 and 7 as the mode select bits of the program counter. This is still a bit wasteful because in most scenarios, we don't really need the program counter to do anything besides just stepping to the next instruction. So once we look at functional units a bit more in detail and how we can further decode instructions, we can then change this. But for now, bits 6 and 7 are just going to be the program counter mode. Alright, pretty sweet. That's the first ROM chip hooked up. And it's going to tell us in pretty nice detail which registers we're reading and which we're writing and how we're interacting with the flags. This is going to be very valuable information in the future when we're building a scoreboard to ensure that instructions can write back to the registers out of order. Now we still need to hook up the ALU and control what it is doing, and we also want to control whether the move mode is enabled over here in the register file and we're actually doing a move instruction. And I think this is where we want to introduce the concept of a functional unit of the processor. Basically, a functional unit is one of the things in the processor that can produce a result of a computation that gets pushed into the register file. Right now we have two of these. We have the ALU, which can write its result back into the register file, and we actually have the move unit down here, which can also write into the register file. Every instruction is going to activate exactly one of the functional units of the CPU, and this is also then the unit which gets granted access to the register file. In the output of the second decoder ROM, we're going to interpret some of the bits as a functional unit index, which is going to select one of the functional units, and the other bits as an opcode that tells the functional unit what to do. We already have quite a few opcodes for the ALU. Remember, this is a 5-bit signal. We can even extend it to 6 bits. We have everything provisioned for that. which indicates what the ALU should do. And then the move unit is pretty trivial, it just has a single operation, it just does its move. I'm going to use a 74HC139 chip, which is a 2-to-4 demultiplexer, so a chip that takes a 2-bit binary value and will produce 4 select signals, and only one of those select signals is going to be enabled, which is perfect for this case because we want to select a single functional unit to do work. Let me use the 2 topmost bits, bits 7 and 6, as the functional unit ID. We'll want to enable the chip constantly. In the future, we might want to use this input to stall the processor if it can't make progress and the functional units shouldn't be enabled. And the 4 outputs that are left are basically our select signals, which we can wire up to the different functional units of the CPU. For example, let's assign the move unit over here, the register file, the functional unit ID 0. And the ALU will assign functional unit ID 1. And we'll basically want to enable the flags and result output of the ALU whenever the ALU is selected. In the future, we might be a bit more fine-grained there and only enable the output that we actually need, but it doesn't make a difference for the ALU right now. We've conveniently made all these select signals active low signals, which aligns nicely with these demultiplexer chips, which also produce active low outputs. Might have even done that on purpose, who knows. The other side of the chip we're not using at the moment, so we'll just tie stuff low. But in theory, we have another 2-to-4 demultiplexer available on the other side, if we come up with a good use for it. Since we're now using the topmost bits of the decoder output to pick a functional unit, we can just connect all the opcode inputs of the functional unit, which currently only the ALU has, to the lower bits, such that the functional unit that gets selected interprets the remaining bits that come out of the decoder as its own opcode, indicating what it should do. Alright, there we go. That's the 5 ALU opcode bits connected to the lowest 5 bits of the second decoder ROM output. One thing that's worth noting is that every functional unit that you can select with the topmost 2 bits gets the remaining 6 bits available as opcodes to decide what it is supposed to do. But for simple units like the move buffer, this is total overkill. These are 6 bits that it is never going to use. One of the optimizations we can do in the future is we can pick one of the output signals of the 2-to-4 demultiplexer and use that as an enable signal for yet another 2-to-4 or 3-to-8 demultiplexer, and then feed some other bits into that demultiplexer. And so basically what this would allow us to do is for most of the 2-bit combinations up here, you get the full 6-bit opcode space, for example, for the ALU, which can make use of it. But then a lot of the other units which are simpler, we can just tuck away behind, for example, the topmost bits being set to 1-1, and then using the other bits here in the decoder output, which would be used as an opcode in the ALU, to actually pick in a more fine-grained fashion which functional unit should execute that op. Right now this is all pretty irrelevant, but if you think about it, once we have a branch unit that controls the program counter, load store unit which interacts with the memory, a control and status register unit which reads and writes auxiliary registers on the sides, maybe interacts with an LCD, etc. A lot of those units won't have as many operations that they can execute. And so a compression scheme like that with additional chained demultiplexers might make sense in that case. But we'll cross that bridge once we're there. For now, let's see if this does something that is more or less sensible. The program will not run as it is because these decoder ROMs, they just contain random data. But we can observe what data comes out of the ROMs and then see if the correct status signals light up on the CPU. Let me clear the reset. So this is the first decoder instruction. Bit 0 is set, which indicates that we're not reading the RD operand. And so none of the read enables are on. Bit number 1 is also set, so we're not writing the RD operand. And none of the write enables are on. That seems to work. Bit 3 is off, which indicates that we're theoretically reading the RS operand from the register file through the read data port 2, but since we're selecting register address 0, which we've reserved and which doesn't point to an actual register, none of the registers are actually selected for reading. And bit number 2 being set means that we're configuring the 4-bit immediate mode, but we're actually not using it in this instruction. Then bit number 4 being set means we're not reading the flags, which we can observe really on the CPU, but bit number 5 being not set means that we're writing the flags, and indeed you can see that the flags write enable is selected. And then the topmost 2 bits are both 0, which means we're selecting program counter mode 0, which is just a regular stepping mode. So when we hit the clock later, it's gonna just advance to the next instruction. And then down here, the topmost 2 bits indicate that we're using functional unit 0. Functional unit 0 is the move unit, and indeed you can see that the move buffer is enabled. And the rest of the bits are just discarded. So a very weird instruction. It's selecting immediate modes and doing moves, but then it's not writing anything into the register file. But this is just random garbage that's here in the decoder. Let me step to the next instruction. This is a bit more interesting. Bits 0 and 1 being set means that we're neither reading nor writing the RD operand, so nothing happens in the first read port and the write data port of the register file. But then the next 2 bits select the RS operand mode, and we're selecting an 8-bit immediate. And you can see that the immediate output enable is on, and the immediate mode is off, which means it's selecting an 8-bit immediate. And indeed, you can see the upper 8 bits of the instruction being produced on the write data port of the register file. And this works because down here we're still selecting functional unit 0, which is the move unit, and so the move buffer is enabled, which pushes the immediate that we're reading from the instruction stream onto the write data port. Next instruction. This one seems to be a bit more interesting. The RS operand is in mode 10, which is the 8-bit immediate mode that is working, and you can see that the RD2 port is set to whatever the immediate bits are in the instruction. But then the topmost 2 bits are set to the value 10, which selects the absolute jump mode in the program counter. And then down here we're selecting functional unit 2, but we have no functional unit connected at index 2, so neither the move buffer is enabled nor the ALU is enabled. So when I now hit the clock, we should see the program counter jump to the absolute value that's coming from the register file, which I think is just address 2, so we're probably in a loop right now. Yeah, there we go. We jumped back to address 2 in the instruction stream, and now we're basically stuck. Let me quickly set the program counter mode to 0 constantly, such that we can just step through a few instructions. So in this case, we're selecting functional unit 1 with the top 2 bits of the second decoder chip, which indeed selects the ALU and enables the flags output and the result output of the ALU. Now, bits 0 and 1 up here are set, so we're not reading or writing the RD operand, so the write data port and the read data port 1 are disabled. But bit number 3 not being set indicates that we're reading a register value on read data port 2, which is what we can see right here. Then bit 4 we can skip for now, but bit 5 being cleared indicates that we're writing the flags. And indeed, you can see that the flags write enable signal here is on, and the flags register would be set to whatever the ALU is producing as output flags. And the lower 5 bits here, which we're using as ALU opcode, actually have the topmost bit set, so this indicates a conditional move. And indeed, you can see that there's a condition match going on here on the ALU, so the ALU is forwarding the right-hand side operand as its result. And if I step through a few more instructions, you can see that eventually we'll arrive at an instruction that again selects functional unit 0, which is the move unit over here, and the ALU gets disabled. So we have an instruction decoder. We have the outputs of the decoder connected to the various control signals of the CPU, and we have introduced a functional unit demultiplexer, which allows us to select one of the functional units through a binary index. I think it's now time to go and figure out what we should write into these decoder ROMs. Okay, let me first create a new directory to put all the decoder related things into. And then let's create a new program to determine the contents of the decoder ROMs. I'm going to use Python for now because that's going to be easy to get up and running. To get started, we basically want to create 2 big blobs of binary data that we write to the disk, one for each of the decoder ROMs. So let's create 2 new empty byte arrays and then write them to disk if what we already have on disk is not the same. Alright, so here we create 2 empty byte arrays that are just filled with zeros for now, but we can later fill this in with data. And then we're calling the write_rom function on both of these byte arrays into 2 separate rom.bin files. And then in this write ROM function, first we're figuring out where we actually want to write this. So we're taking the path of this script, so where the decoder.py script is, and we're finding out what directory this is in, and then we're appending the name of the file that we want. So this ensures that the rom0 and rom1.bin files appear next to the decoder.py script, regardless of where we execute the decoder.py script from. Then if the file already exists, we open it up and read it in its entirety. And if what we've read is exactly identical to what we want to write anyway, we're just going to mention that things haven't changed and that we can skip it. And that's going to be interesting when we make changes to the decoding scheme to figure out if we can leave some of the decoder ROMs in the build without updating because they haven't changed. Otherwise, if we do detect a change or the file doesn't exist, we just open it up for writing as a binary blob, and we just dump the entire bytes array that we have into this file. And when I run this script, we should get two binary files that are exactly 64 kilobytes in size, just containing zeros. Looks like the files are exactly 64 kilobytes. And when we do a hex dump of the file, it's just all zeros. And when I run the script again, we're skipping the two files because the script would just write the same data that is already on disk. Now let's think about how we can actually fill this ROM with data. Since we have two byte arrays here, it's pretty simple. We can just write some arbitrary data into this byte array, and that then gets written to disk. As you can see, the data we've just added shows up here in the output binary file. A ROM is basically a lookup table. In a sense, one of our ROMs can implement an arbitrary Boolean function from a 16-bit input to an 8-bit output. And we have two of these ROMs, so overall the decoder is going to be an arbitrary Boolean function that we can define that takes 16 input bits and produces 16 output bits. One of the ways how we can describe this here in a program is we can actually iterate over all the possible input combinations that we might be feeding into this ROM. So go through all the possible addresses, and for each address call a function, a Python function in this case, with that input, and then we're just going to take that output and store it in the ROM. And of course that works in any programming language. So this is just a cute and convenient way to take a function written in any language you want and actually storing it into a ROM, which is pretty fancy. So we can make this function do anything we want. For example, we could compute the squares of the input. And indeed, when we look at the first few lines in the output ROM, you can see that address 0, when we provide the input 0, we get a 0 as a result, which is the square of 0. Then we get a 1, the square of 1. Then 4, the square of 2. Then 3 squared, a 9. And then 4 squared, a 16, which in hexadecimal is just 1, 0, and so on. So this is pretty convenient. We can come up with any kind of decoding scheme in this function and store it into a ROM in this fashion. I think it would make sense to have this function return a more structured description of the decoded instruction. We can use enums to describe the different control signals we have on the CPU. We have 2 bits that encode the RD operand mode. These are active low signals for reading and writing, so these are the 4 different combinations that we get. By default, we can just make the decoded instruction not use the RD operand at all. Then we have the RS operand. By default, let's have instructions just use the 4-bit immediate mode, which I think is the least contentious, easiest thing. Then we have a similar mode for the flags. And again, we can just not use the flags by default. Then we've also added the program counter mode bits to the decoder. We currently only support stepping mode, relative jump, and absolute jump, but we still can feed a 1-1 into the program counter mode, and this doesn't really do anything proper at the moment, so we just declare it as reserved. And for most instructions, we'll just want this to be in stepping mode, so let's use that as a default. So these are all the signals we've hooked up to the first decoder. The second decoder ROM has the functional unit ID and a micro-op or a functional unit operation field. So let's add an enumeration for the functional unit. We just have 2 at the moment, the move unit and the ALU. By default, let's use the move unit because we have to pick something. And then we also have the functional unit micro-op or opcode. We can just make this an integer for now because we haven't really encoded anything there yet, and different functional units might accept different opcodes. So I think this makes sense. So let's make our decode function return an instance of this decoded class, which contains all the information, and let's just leave everything at default for now. And where we call this decode function in a loop, we now have to take these individual fields of the decode instruction and actually pack it up into the right bit location of where things are connected in hardware. All we need to do is write this pack function. It's probably pretty straightforward. All we want to do is take the value, make sure that only the lowest bits as indicated by the bit length are set, and then shift it up to the right offset. And this here is a very common pattern to get the lowest bits of a number set as indicated by the length operand. On top of this, let me also add a few asserts to make sure that we're not trying to pack values that don't fit into the field that we're indicating. This is all pretty similar to what we've been doing in the assembler when we have been packing up immediate values or register operands. Let me give this a try. As you can see, everything is set to 3f, which is just the default value. So I think it's time to actually go and fill in this decode function to populate these control signals exactly in the same way as we had wired it up manually before. And that should allow us to execute the existing program with the old instruction encoding that we currently have in the CPU. Let me pull up the instructions.architecture file. And right here at the top, we have specified what the individual bits of the instruction were connected to on the CPU. So let's take the instruction bits that we feed into the decode function and plug them apart into these individual fields that we have specified in the ISA. So the lowest two bits were the PC mode. Then we had a bit indicating whether we're doing a move or an ALU operation. Then we had a bit indicating whether operand 2 is an immediate. Then we had a bit indicating whether we're writing the first operand. Then we had the ALU micro-op, which is a 5-bit value, and we've packed this up in a weird way into the topmost 4 bits plus another bit just below. And we had a little bit of logic on the breadboard, which decided whether we should be writing the flags or not, basically by looking at whether we're doing a conditional move and whether the ALU is writing anything. And the conditional move operations are the ones where the topmost ALU micro-op bit is set. So these were the control signals that we've hooked up to the instruction bits directly before. Let's now take these and shove them into this decoded class. Let's set the RD mode to read-write if the write register bit of the instruction is set, and otherwise just to read mode. Then let's set the RS mode to either an 8-bit immediate if the corresponding bit is set, or just a regular register access. Let's set the flags to read-write mode if this write flags condition is set, and otherwise just to read mode. Then the program counter mode we can just copy over from the instruction bits. And then we're going to select between the move and the ALU functional unit depending on what that bit in the instruction is set to. And finally, let's pack up the ALU operation bits into this functional unit operation field we have, because this is where we connected the ALU opcode to on the decoder. I just noticed in the instruction encoding that we were using a 0 to indicate that we do want to write the RD register and a 1 to indicate that we don't. So let me invert this instruction bit. All that's left to do is quickly write up this unpack function all the way at the top. Should be pretty straightforward. Okay, let me run this. And it produces 2 ROMs. This looks like it's doing something. We're producing a wide variety of bytes in reaction to different instruction inputs. And instead of staring at the bytes here, let me actually program these onto our decoder ROMs. And then let's see if the current program we have in the CPU still works. Okay, let's see if this works. The first instruction in our program is a load immediate, and coming out of the decoder, the lowest 2 bits are cleared, which means we're reading and writing the RD register. Then bits 2 and 3 are set to the value 2, which is the 8-bit immediate mode, and we're not writing the flags. And we're selecting the move functional unit down here, and correspondingly the immediate output enable is on, and the move output enable is on. And the second operand is set to 0, which matches the immediate bits in the instruction, and we're selecting the first register for writing. Next up, we have a move instruction, and the decoder produces the lower 2 bits as a 0, which means reading and writing the RD register. Then the RS mode is set to 0, which means we're reading an 8-bit value from the register file as the RS operand, and we're not writing the flags. And again, on the second ROM, the topmost 2 bits being 0 means that we're using the move functional unit, and correspondingly, the move output enable is turned on over here. And since this is no longer an immediate, the immediate output enable is inactive. We're selecting register 0 for reading on the RD2 port and register 1 for writing. These 2 instructions weren't really interesting because the first 2 registers were already 0. But now it's getting more interesting. We're still doing a move, and the decoded instruction here is still the same. So the move output enable is active, but the immediate output enable is inactive. And that means we're reading register R1 on the RD2 port, and we're writing that value back into register R2. Then we have another few moves that clear the remaining registers in the register file. Pretty sweet. So in our existing program, which we haven't changed yet, it looks like our decoder can at least decode the load immediate and move instructions properly. Let's check a few more things. Next up, we have a load immediate instruction, and we're loading the value 1001 into register R0. So this loads the value 1001 into the first register. And now next up, we have a flag swap instruction with register R0. And in this case, the decoder indicates that we're reading and writing the RD operand. We're reading the RS operand as an 8-bit value from the register file, and we're reading and writing the flags. And then on the second ROM of the decoder, you can see that the topmost bits are set to the value 1, so we're selecting functional unit 1 to execute this instruction, which is the ALU, and correspondingly you can see the ALU enable bits here light up. And the lower bits are set to an F-swap operation, and correspondingly on the ALU you can see that the flag swap LED is on. And when I hit the clock, the value from register R0 gets moved into the flags register, and correspondingly the 0 that was in the flags register gets put into register R0. So it looks like we're also decoding the flag swap operation properly. And now we're doing a conditional move from R0 into R1 if the carry flag is set. And as you can see, the decoder selects the RD register for reading and writing. It indicates that we're reading the RS operand as an 8-bit value from the register file, and we're reading the flags, but we're not writing the flags. And then the second ROM selects functional unit 1, which is the ALU, with the conditional move on carry opcode. And so when I hit the clock, you can see that the move from R0 into R1 happens. This makes me pretty confident that the decoder can at least decode the existing instructions that we have in the program. If you remember, we're still computing the largest 16-bit Fibonacci number at the end of this program. So let me just hit run, and let's see if the correct value comes out. Pretty sweet, this is still the value 46,368, the largest 16-bit Fibonacci number. Pretty nice, so we now have an instruction decoder which takes the 16 instruction bits and figures out how to set the control lines of the CPU appropriately. And the decoding scheme we've just programmed into these ROMs is basically just replicating the wire connections we had between the instruction bits and the various control signals. So this isn't really doing a lot of instruction decoding yet. In the next episode, I would like to start and leverage this new abstraction layer between the instruction bits and the processor's control signals. Since we can essentially program any Boolean function into the instruction decoder ROMs, which take the 16 instruction bits and produce 16 decoder bits, we can go back and completely overhaul the instruction set architecture of my CPU. This will finally allow us to bring back that add with immediate instruction we had in the early days of the ALU, alongside a whole bunch of useful new instructions. I can't wait to finally start building out the proper instruction set for this CPU. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you next time.